So welcome. So today, let me get my pen. So today we're going to start on fluid mechanics, and fluid mechanics is divided into statics and dynamics. Well, yeah, we've seen that before. And in statics, the fluid is kind of stationary, and we're dealing with things like pressure and floating or sinking and the like. And in dynamics, the fluid is flowing, and we're dealing with flow rates and pressures again and the like. You can split dynamics into basically laminar flow and chaotic flow. And traditionally, what you find in physics, and to some extent also in engineering, you tend to find that the subjects don't talk about what they're not good at. So it might never occur to you that some things never mentioned, but when you think about it later on, you find out that some things are never mentioned. And traditionally, unless you did a really specialized course, you didn't talk much about chaotic flow at all. And yet weather patterns are all chaotic. If you get high velocity fluid flow, it's chaotic. Turn the tap on and the water just streams out very nicely. Just open that tap up and you start getting sputtering of the water flow. And that's non-laminar flow, it's chaotic flow. We still don't talk much about it, but at least we point now in its direction and say, well, there's math over there that will take care of that, But it's an upper division course as opposed to a lower division course. So on this first bit, we're going to talk about pressure, a thing called Pascal's principle, which is the basics behind hydraulic systems. And then we'll talk about buoyant force and Archimedes' principle. And then at the end, we'll talk about fluid dynamics. And there's a couple of equations there. There's the continuity equation, and there's Bernoulli's equation. So two equations are going to come out of that. So let's start with the statics bit, and we're going to talk about just the concept of pressure. And pressure equals force per unit area. So a medium force over a tiny area is a big pressure. A massive force over a large area is a big pressure. It's basically, there's a ratio between these two things. And so sometimes you can affect pressure by focusing on the area and trying to minimize that, or you can affect pressure by focusing on the force and trying to maximize that, whatever you want to do. Pressure, the SI unit for pressure is in Pascal, and Pascal is 1 Newton per square meter, per meter square. Per square meter, sorry. So, but that's in the SI unit. Inches of water, well, what's going on with that? It turned out that we used to measure pressure most conveniently by using what was called a U-tube manometer, which we'll get to. You put your gas bottle on here and you connect it, and you open the valve and you see what it does. And the water started off being level, and then what happens is the one end gets pushed down and the other end gets pushed up, so you end up with like a J shape, and you look at the difference in the height. And the inference is that the bigger the pressure here, the bigger the change in height there. So I can characterize the pressure by the height. And so that leads me to inches of water, millimeters of mercury. The problem with inches of water is 1 atmosphere is a tremendous number of feet. I mean, I can't remember actually. It's something like 20. I think it's like 22 feet or something like that. But that's a big meter you need just for 1 atmosphere. We can make it a smaller instrument if we just use denser stuff. So use mercury. Mercury you wouldn't see used these days. When I was a student, they used to pass it around class. They'd open a bottle of mercury and pour it in your hand, and you just it's fascinating. I remember it would run all over the desk, and you'd pass it to the next person, and by the end there was none left, kind of thing. That would close a school down now. That would be a huge issue. And for those people who are literary, you probably read Alice in Wonderland, and they have the Mad Hatter, and it's common terminology, Mad Hatter. It comes from a fact, actually, that back in the day when they had felt hats, you can't just brush a felt hat. It shows the gleaning process. It's so delicate. So what they'd do is they'd use some kind. It's like the precursor of dry cleaning. They'd use some kind of material which would, as a vapor, go into the cloth and attach itself to the dirt particles, and then draw the dirt particles out. And mercury was great for that. So they'd have pans full of mercury, and they'd like hang the hats above it, and the mercury would, the material would clean the felt hat without really brushing against it, and so the hat would look pristine and clean and everything. And what people noticed was, as hatters got older, they got really eccentric. I mean, more eccentric. Old people get eccentric, but they get really eccentric. And then eventually they found out that they were getting mercury poisoning because they'd be in a little office, and they'd have this thing. So mercury's great. You can have a small instrument. My grandmother had a barometer on the wall. It was you can't think of what present to buy somebody. You buy them a little barometer, the fair, foul, sunny, whatever. They'd have a temperature on one side, a barometer on the other. It would be full of mercury, and no one thought anything of it. So these are basically using this U-tube manometer as the mechanism for characterizing pressure. But pressure is really a force over an area, and so we have pounds per square inch. That was the imperial unit, and more commonly Pascal. I used to work in vacuum science, and although vacuum science is taking gases away from things, you characterize the quality of vacuum by the amount of pressure inside the system. And I remember counting up at some time there was something like 12 different scales that were used in industry for pressure. Because different industries have different traditions. So if you buy high pressure gas, it'll probably come in pounds per square inch. But if you go and buy an instrument that's for evacuating things, it'll often talk in terms of torr, which are named after Torricelli, who was a famous Italian vacuum scientist, I suppose you could call him. And that's a millimeter of mercury, so it's back to that. But there's bar, millibar. You've got to look at the weather. They're also using pressure scales. So different areas had different units, and they're still not standardized. And that's kind of the way it goes. Okay, so pressure is force per unit area. When a pressure is created when an 80 kilogram person balances on a 4 millimeter by 4 millimeter heel. So here's my 80 kilogram person, and we'll have it balancing on a 4 by 4. So my mass is 80, which means that my weight is 800 newtons. And my area is 4 millimeter by 4 millimeter. Now, I'm being careful here. It's not 4 square millimeters. It's 4 by 4. It's 4 millimeters that way and 4 millimeters that way. And if you count up, that makes 4 by 4. That's 16 square millimeters. 4. So this is 4 millimeter squared. And this is 4 millimeters by 4 millimeters. Can you see the difference in the language there? So you've got to be careful about that. But this is 4 by 4 millimeter heel. And so we say, well, pressure is equal to the force per unit area, which equals 80 times G, let's say that, 80 times 10, over 4 times 10 to the minus 3 times 4 times 10 to the minus 3. So this is going to be 800 over 16. This is where you do multiply the two together. 16 times 10 to the minus 6. Okay. So this is going to be, that goes into that 50 times 10 to the 6, which is 50 megapascal. Visualization. Pascal is a Newton per square meter. Agreed? Take an apple, put it in a blender, pour whatever you get into a frame that's 3 foot by 3 foot. Imagine the pressure felt underneath that frame. It's tiny. Pascal is a tiny amount of pressure. A atmosphere is about 100,000 pascals. Atmosphere is like taking 100,000 apples, blending them, pouring them into a frame of, imagine it, trying to hold up 100,000 apples. This is 50 million apples in that 3 foot by 3 foot frame. It's quite a considerable force per unit area, actually. This is actually, it's intriguing, actually. When I was about 15, we moved from a schoolhouse that my mom had gone to school in. Actually, I had a teacher who my mom had taught, who had taught my mom. It was kind of interesting. He was an older guy, and we saw him as the guy who was like beyond retirement, couldn't remember anybody's name, And my mom had clearly been taken with him when she was a schoolgirl, and when she'd meet him, she would just this aspect of my mum would come over. She would be kind of like a bit distracted by him, and he was an old guy, but she still had that your teachers are your teachers, even though my college teacher is 10 years older than me. He's 70, I'm 60, and yet I still defer to him. Two old people, and one's deferring to the other, because the relationship doesn't go. So it's kind of interesting. Then when I was 15, we changed schools. And in Britain, they have not auditoriums, but they tend to have halls. And we had a circular hall. It had a stage at one bit. And when they wanted a play, they'd put chairs out and we'd have a play. And when they wanted a dance, they'd put a band up here and we'd have a dance. When they wanted assembly, we'd all stand here and listen to the talk. And when we had parents' evenings in Britain are very different, certainly in my experience. They put all the teachers' desks around the edge of the room. Every teacher. And then what they do is the parents come in, and the idea is, the parent can see the teacher, but the teacher can also see the parent. Because often it's the parents that don't come to see you that you want to talk to. So the idea was the teachers were scanning the room looking for parents to kind of collar, and then the parents would form lines in front of the desks to talk to the individual teachers. So it's kind of like almost like a marketplace with, little hushed conversations about, your kid and, all that. And it's kind of interesting. But what they did was they had a big sign outside, this big bucket, and what they had was they had these little plastic heel protectors, they called them. And for women's shoes, my mum's of that generation where she would have worn stiletto heels to the gym. She basically wore stiletto heels every day of her life. They were only small stiletto heels. They were maybe like an inch tall, but they came down to a little clip, and that's just what she wore. And so if you got a whole bunch of mums walking around the place with these little 4mm by 4mm heels, my mum's heels were like probably 2 millimeters in diameter. They were really quite small. And they would have put pepper marks all over the floor in no time. And so they used to put these little heel protectors just to spread out. If you make the area 12 times greater, you get 12 times the pressure. 1/12 the pressure, so it really helps. I've only ever seen these advertised over here for like weddings. It turns out people have weddings on lawns, and yet people want to wear high heels, and so they sell these things for weddings. That was the only advertisement I could find for them, for that. My mum once stepped on me when she had her high heels on. And she stepped right where my big toe began. And I was crippled. And she was not in the least bit sympathetic. She says, you've got to keep your distance, you know. We had a tiny kitchen. She goes, oh, these are my best friends, because public transport's great, but your body's, you know, you have no space. It's like you are right next to people. And she goes, people get too close. I just lean back and put my heel on their toe, and they move real quick. So it's interesting. Thanks ever so much. What's the pressure exerted by a right cylinder that has a radius? So now I'm making it a bit more interesting. Radius of 2 meters, height of 4 meters, a density. Okay. So now you've got to work a bit harder for it. So it's kind of like, okay, here we have the mass. So pressure is equal to force per unit area. And my force will be the mass times g, of course. So my area, now it's a circular area. So it's going to be pi r squared. And then I'm going even a little bit further than that, in that I'm going to say, well, my pressure, which equals my mg over pi r squared, I'm not even giving you the mass, am I? I'm giving you the density and the volume. So my mass is equal to my density times the volume. Agreed? Kilograms per cubic meters times cubic meters gives me kilograms, times g over pi r squared. So I can make it a bit more interesting. And then I come up here and I go, a cylinder as a density. So that's 8 kilograms per cubic meter. It's helping me there. And then my volume. My volume is going to be, well, actually pi r squared times h. Let's hold off on this. I'm putting numbers in just for a second because something very nice is going to happen. So rather than volume, I'm going to have pi r squared times h times g over pi r squared. So that's interesting. So then I can cancel out, that guy goes with that guy because it's the same pi r squared. So my pressure is equal to rho g times h, which equals my 8 times 10 times height of 4 meters, which equals 3 it's a 24, 4 it's a 32, 320 Pascal. Now in this case, I gave you enough information that you could, even if you didn't spot the fact that the area cancelled, you could still work it out. But I could ask this question and not give you the radius, in which case you wouldn't be able to work out the volume because you don't have the area, and you wouldn't be able to work out the area because you don't have the radius. And so if you don't think in sentences, if you just think in catches, phrases, volume, that's going to be pi r squared times h. Area. You might not catch the fact that it's cancelling and that you don't need the radius because the radius cancels. And so you might think I can't do it. And that's part of the tradition is to check, are people thinking in terms of complete sentences? Reward those that are because you see it cancelled, and for those that don't spot it, hey, that's an insight you're not getting. So watch out for stuff like that. So this is another type of problem. Consider a shape-shifting object. Like Mercury is a shape-shifting object, has a certain volume, but you can change the shape of it. That can change its footprint area, but not its mass. Student calculates the pressure that an object exerts on the floor for different footprints. So I can imagine, take this thing like that, and then take the thing like that, and then take the thing like that. So I have different areas, but I have the same amount of stuff. Assume appropriate values for the relevant parameters, write governing equation, make the data table, plot complete graph with at least 3 points. Oh man, what do I do here? Well, I'm plotting a graph. What shape should the student calculates pressure so it's pressure, should have been clear about that actually, that an object exerts for different footprint areas. So it's pressure versus area. And so what I need, let me just erase this a little bit. I'm going to get rid of some of these because you don't need all that. So, you know, we could have a little one, or we could have a, that tells me the same thing, okay? So I say, well, let's have a look. Pressure is equal to the force per unit area. And the force is equal to mg per unit area. So P is equal to, well, m's not changing. Let's just write that down. And g's not changing. For all of these, m's the same because you're not losing or gaining stuff. And you're not losing or gaining gravity. You're not moving it in the gravitational field. So that's going to be that. Now, some people can say that's an inverse. They can just look at it and say that's an inverse. Other people, they need a bit more work on it. So the trick now is you put down your two things. And now you've got to mech stuff up. People are very uncomfortable meching stuff up. I'm going to say that m is equal to 1 and g is equal to 1 because there's no law saying I can't. And I'm going to say 1 over a. So I'm just deciding. They're constant, so call them 1 each. I might as well decide that. And then I go, well, let a equals 0. If a equals 0, then that's 1 over 0, which I think is infinity as far as I'm concerned anyway. And then let a equals 1. 1 over 1 is 1. Let a equals 2. 1 over 2 is 0.5. A equals 3. 0.3. Okay. I know where this is going. 4. 0.25. Agreed? So now I come along here, go 0, 0. I want to go as big as, well, infinity is a bit much, but we'll go as big as 1. 0.2, 0.4, 0.6, 0.8, this is 1. There. Then on this side, I want to go as big as 4. Back 0, 1, 2, 3, 4. Might as well go that. Put down some, well, it doesn't matter about units, but put down meters squared and put down Pascal, whatever. Yeah, whatever. And then I go, well, 1 and 1. So that's 1 and that's 1. So there's my first data point. And 2 and 0.5. So 2 and 0.5 is my next data point. 3 and 0.3. So 3 and 0.3. And 4 and 0.4. 4 and a quarter. And so that gives me a nice curve. And that is the next level of skill. We've done before, can you pick the right, pressure versus area? And you've done stuff like this, haven't you, where you have that series of graphs and you go A, B, C, D. Remember that? That's one level. Can you recognize that it's inverse? Can you recognize that it's a parabola? What can you do? But the next level is, are you comfortable making numbers up for yourself? And often people are not comfortable. And yet, in real life, you're not going to be always given, find the answer to this. You're going to have to think about it, even though there's, the parameters are wide open to you. You go to a construction site, no one's marked out the parameters. You've got to mark out the parameters. You've got to decide on things. So it's part of that skill. Okay, so that's the next level of skill that's coming in. And then I'm just looking at the time. And then a system consists of a right cylinder resting on ground. The cylinder exerts 5 Pascal pressure. What would be the pressure of another right cylinder that had a height that was 4 times greater, a radius that was twice as big, and a density that was 3 times greater? So I still like to visualize. So here's my first one. And I don't have to be precise about it. Where the height was 4 times greater, I'm going to do it like that. And, radius was twice as big. Oh, my word. Sorry about that. And then density, it's even different stuff. Oh, my word. There's different stuff in here. Okay. So the key thing is 2 things. What's the equation? And it's going to be, we're talking in terms of what would be the pressure of another right cylinder that had a height, radius, and density. So that's what I'm looking at. And so pressure is equal to force per unit area. And so the force is going to be the mass times G times area. And mass is going to be the density times the volume times G times area. And so this is equal to the density times the area times the height times G over the area. So this is rho GH. And people know rho GH. It's like, you know, they get to the stage where they don't have to do that derivation. But you can if you need to, you know. I'm just reinforcing with myself where it comes from, you know. Oh, pressure. Got to be careful now. Okay, so there's another little background lesson of when you have two symbols that look similar, make sure they look different. There's nothing in the world saying you can't make this a nice fancy big P whenever you write pressure and make the density clearly different. Because I will get people and they will just get confused and they'll cancel pressure with density and stuff like that. That's because they know the equations, but they don't know the equations, if you like. They kind of don't know what they look like, but they're not really sure what they mean. So you can write them out as long as they're recognizable to me. You can't put down gamma for pressure because you decide you're going to call it gamma so you don't get confused. Then that's very confusing, you know. But you can embellish your letters to make them clear. Okay, so this is a ratio problem. It wants to know what would be the pressure. So P new over P old is equal to P new over, and put down your old pressure. A system consists of a right cylinder resting on the ground. The cylinder exerts a pressure of, that's the old pressure. And then write it out. Density new, G new, H new, over density old, G old, H old. And that equals, now look at your words. What would the pressure of another right cylinder be if the height was 4 times greater? Oh, well, call the new height 4 and call the old height 1. That's the simplest way of making it 4 times greater. The radius is twice as big. Well, actually, radius is not in my equation because area is not in my equation, so I don't need that. And the density is 3 times greater. So my density is 3, the new one is 3, and the old one is 1. And that leaves this G. G's not mentioned, so G's not changed. I could have gone to the moon, but I didn't, you know. So you got a choice. You can either put G over G and cancel it out. Or I get in the habit of just calling it 1. If you don't know what it is, call it 1. But either way, both are correct. It's just what are you comfortable with. So P nu over 5 is equal to, well, that's going to be 12. So P nu is equal to 12 times 5, which equals 60 Pascal. So it's that answer. And that's, first of all, you know, you don't always have the absolute values. You know that you turn something up to twice as much, or you make something half as big, or so. I suppose you could invent numbers for each of these things and do a complete calculation and then do some other calculation. But it's quite often you're going to just know the ratio of how things change. And this is, in a way, quite sophisticated because, I mean, in terms of question, from a teaching point of view, I'm giving you a red herring, I'm giving you the radius, even though it's got nothing to do with it. If I make the radius bigger, I make the area bigger, which it nullifies the effect, you know. My mind's going through things. Okay, cool. Okay. Okay, so now onto some of these gauge type things. So this is a glass of water. And some terminology, first of all. The glass of water is open, so there's pressure pushing down on the liquid from the atmosphere. Now we're going to take that into account. And then there's the pressure at a certain depth within the water, and that's called the absolute pressure. And that is caused by two bits. It's caused by the pressure caused by the pressure caused by the water above it, and it's also caused by the pressure caused by the atmosphere above the water. We call the pressure caused by the fluid the gauge pressure, because that's what we use to gauge the amount of pressure. We talk about the difference in the height of the fluid. So the pressure caused by the fluid is the gauge pressure. So we'd have absolute pressure equals atmospheric pressure plus gauge pressure. And then it turns out that the gauge pressure is, well, it's going to be the force per unit area, which equals the mass times g over the area, which equals the density times the volume times g over the area, which equals the density times the area times the height times g over the area, which equals rho gh. So we know where that comes from. Yeah? So our gauge pressure is the rho gh. So we have P absolute is absolute pressure, P atmosphere is P atmospheric pressure, rho gh is the gauge pressure. And just so you know, 1 atmosphere is 101 Pascal, 101,000 Pascal, basically. Barrel is filled with a fluid that has a density of 4 kilograms per cubic meter. Barrel is open to the atmosphere. The atmospheric pressure is 8 Pascal. What's the absolute pressure? 3 meters below the surface. I'm going to stop. We've not got the clickers. I assume we're mostly done. So basically, we made a list, and that jogs our memories, and we did a diagram. That really helps. And we can say pressure equals force per unit area, which equals m times g over area, which equals density times volume times g over area. So pressure is equal to the density times the area times the height times g over the area, which equals rho gh. And there's nothing wrong with just remembering that pressure is equal to rho gh, because you're going to use it a lot. So now we just turn around and say, okay, well, pressure is equal to my rho, and my rho is 80 Pascal. That's a really low pressure, times g, and my g, we're on Earth, so g is going to be 10, and my h, in this case, my h is 3 meters. Oh, I'm sorry, shame on me. P absolute is equal to P gauge plus P atmospheric, and P absolute is equal to rho gh, because that's P gauge plus P atmospheric. So P absolute is equal to 80 times 10 times 3 plus my, I've made a mistake here, haven't I? 4. This is 4. Duh. So can you see, what did I do there? A P and a rho can be easily confused. So I did my own thing about misreading my own stuff, because I didn't know my equation as well as I should have done. So this is density, which is 4, plus 80. So P absolute is equal to 4 3s are 12, 120 plus 80. I think it's going to equal 200.
Quick question on this one.
Yeah.
Because the 3, it stays positive because it's just an absolute value of it, or is it because the direction of the measurement?
It's not a displacement, it's a height. Okay.
That's why I'm asking, because it says below the surface, because if you read into that, you've had questions before, if you said below, now it becomes negative instead of positive.
Because it was a displacement, but this is not a displacement. This is the height. So it's contextual. I mean, there's...
Height is always an absolute.
Pardon?
Absolute value.
I'm sorry?
Height will be considered.
In this context, when I talk about below the surface, it's just talking about, I mean, you can say from your terms of reference that you're interested in the pressure at that point. Okay? So from that point of view, if you look at the diagram, from that point of view, then this is above where my reference point is. Okay? So this is below where the reference point is. This point of interest is below. This point of interest is below the surface. So again, you got to go with the language of it. Yeah, it's like. Okay, two very traditional pieces of apparatus. You won't see them in the labs almost any time. Maybe a teaching lab. You don't measure pressures using these things. I've not seen them used in anger for years. I mean, you can just buy a little pressure head, and that will give you electronic readout of the pressure, But so U-tube manometer is basically you have a high or low pressure here, and it either pushes or pulls on the pressure. So vacuums don't pull. It's the atmosphere that pushes. Now, in this case, this pressure is greater. So this is pushing down harder than this side is pushing down. If I made this one lower than atmosphere, it would not be that this is sucking. It would be it's pushing down less than the atmosphere is. But there's a common misconception that vacuum sucks air in or whatever. It doesn't. It's just it doesn't push out as much as the atmosphere pushes in. Okay? So, although colloquially we talk about pulling, it's actually all pushing. So we have the pressure of atmosphere because there's an open tube on that end, and we have, the pressure of my test must equal my atmospheric pressure plus my gauge pressure, because it's that change in height. Plus there's also this atmosphere. And on a high pressure day, it's pushing down more than in a low pressure day. So that will affect my results. And then people said, supposing I could get rid of this atmospheric effect, supposing I could just have the gauge pressure, well, that would mean having no atmosphere above this side. Can I do that? And you can, actually. If you take a bath of water and you turn a glass upside down in it so the air escapes, and then you turn the glass the right way around, it's full of water. And then as I raise the glass out, this stays full of water, and it stays full of water. And eventually you get to the stage where the water level will not get any higher, no matter how much you raise this out, as long as you keep the seal. There's a certain level above which the water will not go. And so what's in this space? Nothing. Really, there's a fair bit in that space, actually, but in terms of, amount of atmosphere, there's nothing in that space. So we call it a vacuum. And why is it at this steady level? Well, because the atmosphere is pushing down, P atmosphere, is pushing down with a certain amount, and that's balanced by only the gauge pressure, because the bit here is gone. So I suppose I should actually, because let's just talk about that. If I could make a U-tube manometer that was sealed. So I still have P-test. I have my P-gauge. But I have a vacuum here. So it's the same apparatus, just sealed off this end and made it a vacuum. Then this equation will become P test equals P gauge, because we got rid of the atmosphere. Agreed? But where this is most commonly used, in the past anyway, was in a barometer, and the barometer was there to measure the atmospheric pressure. And so what they do is they get rid of the P test bit, and they just break the glass here. And they say, oh, now I have P atmosphere here compared with P gauge. And so in this context, you get P atmosphere equals P gauge. So these are not quite the same. These are not the same apparatus, and so the analysis is a little bit different between them. In this case, we say that P test equals P gauge because we got rid of P atmosphere. But when we make a barometer, we're not using P test, we're using the system to test the atmosphere. And so we end up with P atmosphere equals P gauge. So at first glance that can be a bit confusing because here P test equals P gauge and now we have P atmosphere equals P gauge. But in this case what we're testing is the atmosphere. Yeah? So they're commonly used. When I took over the labs at USF, we probably had 25 huge mercury-filled barometers, and to dispose of them, we had to get basically safety in to dispose of them. And when we refurbished that room, there was little drops of mercury that were just under the tiles, basically. Disaster. Somebody had broken one, years ago, and the mercury had stayed there. Now, it was a storeroom, so it was okay, but when I worked in industry, let me just pause for a second, because this is just... Okay, so open tube manometer is filled with fluid that has a density of that. A cylinder of compressed gas is connected to the end of the tube. It causes the height to change by 4 meters. The atmospheric pressure is that. What is the value of P test? P test is equal to P gauge plus P atmosphere. P test is equal to rho GH plus P atmosphere. P test is equal to my rho 6 times 10 times my H plus P atmosphere. P test is equal to 240 plus 300, which equals 540 Pascal. Cool. So mathematically not that challenging. It's just multiplication and addition, but got to know which bits to add up and which bits to not add up. Barometer is filled with the fluid that has a test density of. So I actually like to draw my barometers like that because it's a bit more reminiscent of the U-tube manometer. So this is vacuum, this is H, and this here is P atmosphere. And it says, what is the atmospheric pressure? P atmosphere is equal to P gauge, which equals rho GH. So P atmosphere is equal to, do I have a density? Yes, I do. Do I have a G? I know G. Do I have an H? H is 5. P atmosphere is equal to 400 Pascal. Which is there. Occasionally, you will see not the mass density, which is typically called the density, but the weight density. The mass density is in kilograms per meter cubed. And the weight density, I like to call it, that W, is equal to the newtons per meter cubed. Because it's the weight density. It's not how much mass is in it, but how much does it weigh. And the weight density is equal to the density times G. Can you see that? You go from kilograms to newtons by multiplying by G. W is equal to mg. So if you want to go from the mass density to the weight density, you've got to multiply by G. And so here, if I'd given you the weight density rather than the mass density, you would not have had rho GH. You'd have rho W times H, because the G's already in it. Okay, so watch out for that. That sometimes happens. Not a lot, but it sometimes happens. Okay. Pascal, we are still on statics, though slow motion. We basically, to get what we want, you take your car to the lift, you take your car to the gas station to get it repaired. They put it on a lift and they press a little button and the thing rises up. What they've got is a hydraulic system, and the hydraulic system is basically a mixture of big round pistons and small narrow pistons. And there's this so-called Pascal's principle, which says that the pressure is the same at all points inside an enclosed fluid. Now this fluid is enclosed, there's no air inside here, it's just oil typically. So the pressure P1 is equal to the pressure P2, which means the force per unit area. So F1 divided by A1, F1 over A1 is equal to F2 divided by A2. Now, if you think about it, a little pressure on a little area balances a big pressure on a big area. So that means I can push on a little piston with my thumb and have a huge force on a big piston. In principle, I could balance my car with my thumb. And it seems like you're getting something for nothing, but you're not. You're just equalizing the pressures. Sorry, it's my... Sorry.
I found something on the web about how do you say would like to get some...
Yeah, sorry about that. Sorry. Now, you're not getting something for nothing. Let's say you lift your car up. Let's say you have the piston for your car, and you have this little piston, and you want to lift your car up. That's a man's work. That involves doing work. You have a force, if you like, a lifting force times a distance. Huge lifting force, small distance. That's balanced by actually moving this force here, the pushing force, through a huge distance. Because the volume of this fluid, if you think about it, has to balance the volume of that fluid, because you don't get a lift out of nothing. So you end up pushing this little force a long way. So the amount of work you do in lifting the car is the same amount of work you do by lifting it. But like simple machines don't change the amount of work you do. They change a little force through a big distance for a big... They change a big force through a little distance for a little force through a big distance. That's what pulleys do, that's what screws do, that's what ramps do. You change a big force through a small distance for a little force through a big distance. Because we've only got a limited amount of force we can exert, but we can do it for a long time. That's the amazing thing about simple machines. So we're not gaining anything. It's not like it's an engine. We're just making the forces more manageable. But it's amazingly valuable. So a typical question, hydraulic system consists of one cylinder as a cross-sectional area. So that is 4 square meters. Connected to another cylinder. Doesn't matter, but I like to try and get them the right way around. That's 12 square meters. A force of 9 newtons is applied to the smaller cylinder. What force acts at the larger cylinder? So you can say what force acts here or what force would balance it. It's the same thing. What force are you getting here? So I say P1 equals P2. F1 over A1 equals F2 over A2. So I look at my diagram and I go 9 over 4 is equal to F over 12. So F is equal to 9 over 4 times 12, which equals 27 newtons. 4 goes into 12 3 times, 3 nines are 27, 27 newtons. How can I make this a bit more interesting? I can make it a bit more interesting by giving you the radii. So now you've got to do F1 over pi R1 squared equals F2 over pi R2 squared. So now we're changing, not a simple ratio of the numbers. Still just the same thing, but I'll just make it work for it a little bit more. I can, rather than telling you the force, I can tell you the mass I put on here. And you've got to figure the force out, mg. There's just lots of ways I can just make it a little bit more interesting. I want to get ahead, so I'm going to that's just a repeat of the same thing. Okay, so now we're going to go to the topic of floating or not floating. And basically, let's picture, there's two cases, floating or not floating. Let's say you're not floating. It's the simpler case. Well, it's not simpler. It's about the same, actually. If I am under the water, I have displaced some of the water, which is now on the surface. Otherwise, I would be on the surface and the water would be lower. So there's a fight between the water being below and me being below. Yeah, makes sense. So that leads a buoyant force. If you like, the displaced water is pushing me out. That's the buoyant force. That's when you go swimming. That's the force that pushes up on you. And then there's the weight. You've still got the same weight when you're in the water as you do when you're not in the water. Gravity's still pulling on you, so you still have the same weight. So when you are submerged, when an object is submerged, there's two forces acting on it, the buoyant force and the weight. And I try not to talk about buoyancy or the force of buoyancy and all that, because buoyancy is a colloquial term and it means the net effect. How does your buoyant force compare with your weight? If you have a lot of buoyancy, then your buoyant force is bigger than your weight. If you don't have much any buoyancy, then your buoyant force is less than the weight. But I try not to talk about that. I just try and talk about buoyant force and weight. And I know, well, let's think about this. The force is going to equal mg, which equals the density times the volume times g. So there's the density of the fluid, there's the g, and there's the volume of the displaced fluid. So that's where that comes from, rho g v. We had before the pressure is equal to rho gh, and now we've got force is equal to rho gv. So again, as always, when you get things that are similar enough to be confused, put them down side by side and distinguish between them. Don't get them confused. A casual observer will get these two confused all the time. So there's a danger of that. So make sure you don't by putting them down side by side and saying, hold on, how can I tell the difference between these two things? Or can I learn the difference between these two things? Set an alarm bell so that when you get uneasy around this bit, because I might get it too confused, I've got to make sure I don't use the wrong equation, rather than using the wrong equation and not realizing it. You've got to prepare. And if the force is that, then the force of gravity is the density of the object times g times the volume of the object. The weight is all about the object. I try not to use the term block anymore, because block and buoyancy both begin with B. So I try and talk about objects. The buoyancy is all about the fluid, because it's the fluid that you're pushing higher in the glass. So it's all about the fluid. So the buoyant force is all about the fluid, which is the density of the fluid times G times the volume of the displaced fluid. Now, when you are completely submerged, what can you tell me about the volume of the object and the volume of the displaced fluid? Just look at your diagram. They're equal to each other. So by definition, when you're submerged, completely submerged, those two are equal to each other. When you're floating, that is not the same. Okay, we'll have another rule for when you're floating. This is conceptual. It's a little bit of a trick question. Picture. Let me just have a quick look at my time. Picture throwing a cubic meter of lead into a swimming pool. There's my cubic meter of lead going in. Picture throwing a cubic meter of styrofoam into my swimming pool. Which has the bigger buoyant force? I'm going to pause here for a second. So yes, ironically, because the lead sinks, it has a bigger displaced volume, and so it has a bigger buoyant force than the styrofoam, which floats on the surface and only displaces a little bit of the fluid, and so has a smaller buoyant force. Remember that the buoyant force is all about the displaced fluid. It's not about the object. It's about how much fluid do you displace. I'm going to stop there. Let me have a quick look. Yeah. I'm going to stop there. We're going to take a 5-minute break.